Welcome DP Sogong aboard. Your learning journey starts now. Ever felt like P versus NP is a riddle wrapped in an enigma? Forget the usual suspects for a second. What if the real question isn't just can we find it quickly, but what is the thing we're looking at fundamentally? This isn't your grandma's complexity theory. We're diving into the semantic guts of it all. So where does this new proof live? Not in the land of Turing machines or polynomial time directly. It lives in semantic space. Think of it as the ultimate reality check. Here, the complete object isn't just the input x, it's the full package, x, w, the input and its witness. Conceptual space squishes this into neat labels like p and p, and that existential quantifier exists w. Symbolic space then builds the machines and formulas. But here's the kicker. Projecting from the complete relation x, w down to just x throws away crucial information. It's like describing a sculpture by only showing its shadow. It's not the same thing. Okay, let's get specific. We've got two main ways things close semantically. First, the p-type. You start with x, and everything needed to decide yes or no comes from within x's own relational world. It's self-contained. Then there's the NP type. You start with the whole shebang x and w, the completed relation. The verifier just checks if this pre-assembled thing works. See the difference? One builds internally, one verifies externally. They might give the same yes or no answer, sure, but they're operating on different fundamental levels, different starting points, different ontologies. It's like comparing baking a cake versus checking if a cake is already baked. Now for the big reveal why these two closure types can't be the same. Enter the projection non-substitution theorem. Imagine trying to perfectly map the world of complete relations YR back to the world of inputs X using our projection pi. Lemma 1 says X multiple valid witnesses W1, W2, then pi sends both X W1 and X W2 the same X, boom. Pi isn't injective, it's many to one. Lemma 2 adds, even if you cleverly pick one witness S of X to get back to X, you're only picking one representative. You lose all the other possible completions. So, no perfect two-way mapping preserving everything can exist. The projection simply doesn't hold the full ontology. And so we arrive at the main event, the semantic non-identity theorem. PSEM, the class of problem solvable via input endogenous closure, is not the same as NPSEM, the class verifiable via completion verification closure. Why? Because their starting points are different, x versus x, w. Their domains are different, x versus yr, and their generative dependencies are different. Finding a polynomial time algorithm for SAT wouldn't make them identical, nor would proving superpolynomial lower bounds. This is about the fundamental structure of the problem-solving process itself, not just how fast it runs. It's an ontological distinction, pure and simple. So what does this mean for the famous P equals NP question? It means that asking whether P equals NP in the traditional sense, focusing on language classes under Turing machines and resource bounds, is a different question altogether. Our semantic proof shows that the underlying processes, the ontologies, are distinct. Whether conventional P equals NP holds or not is still open, but it doesn't negate this deeper structural difference. It's like saying, even if you find a super fast way to bake a cake, it's still fundamentally different from just checking if someone else already baked one. The core inside simulation is not reality. That's the semantic twist.